All right. What's number 1 says? Consider the section of roller coaster depicted in the diagram. A 100 kilogram car moves along a frictionless track and comes to a stop as it compresses a huge spring at point D. It's huge. Okay. How much energy is in the system?
So we got 30,000 joules, and how we got that? Well, first of all, at point A, it has gravitational energy involved, and at point B, some gravitational and some kinetic. How we got it is we used the gravitational energy equation, plugged in our numbers. That's how we got it.
Yeah, so the key to this one is at A, okay, at A, it's all gravitational. So if you can calculate that, you're going to know how much energy there is in the whole system, regardless of what it looks like. All right, now that brings us to number 2. Number 2 says, well, how fast is the car moving at point B? B is in boy.
Well, it first starts out like gravitational, so then we have to plug in the numbers, and then we get 10,000, and then we put it there, and then we had to find kinetic too. So we plugged in the numbers again, and then solved for it and got 20 meters per second.
So what I like about this one is, what's your total amount of energy in the system?
Total amount is 30,000.
It's 30,000, right? And at point B, it's 10 meters off still 10 meters off the ground, right? So you can find out how much gravitational energy there is, which is 10,000. You can see that in the bottom right-hand drawing there. And so if 10,000 is gravitational, then what's the rest? 20,000, and that's got to be the kinetic, right? And then from there, you just solve for speed. 20 meters per second. That seems really reasonable. All right, does that match what you guys have? All right, fantastic. Let's do the next one. All right, what's it say about the spring?
The spring at point D has a spring constant of 5,000 newtons per meter. Write one sentence and describe the spring constant.
Okay.
Well, it was 5,000. We just had for every statement, for every 5,000 newtons of force, the spring will compress 1 meter.
So that's not too bad. Normally when we write for every statement, we use the denominator first. So it's really for every additional meter that you want to stretch or compress the spring, it's going to take an additional 5,000 newtons. But I think you have the right flavor here, right? If you want to compress it 1 meter, it's going to take 5,000 newtons. What if you want to compress it 2 meters?
10,000.
10,000, that's right. There's a linear relationship there. What if you want to compress it 3 meters? 15,000, that's right. So that linear relationship there is important. Cool?
Yep.
All right. What happened to 4? You didn't finish it.
They didn't. That's
We
their
did
fault. Number 4, how far does the spring compress? How far does the spring compress while bringing the car to a stop? They erased the answer, but it was, you erased it.
I erased it.
It was 2 meters.
How do you know it's 2 meters?
Because how I figured it out was at point A, you had it all gravitational, and it was 30,000 joules. And at point D, it's at 20 meters, so it's 10 less than it was at point A. So we found that it was, that 10,000 to 30,000 joules has gone to kinetic energy, because it has less height, so it had to go into something else. No, wait, no, not kinetic energy, I meant elastic energy. But because it has less height, it has less gravitational energy, and it had to go into the spring, so the 10,000 joules went into the elastic energy.
Okay, so this sounds really good, right? What he's saying is 10,000 joules is elastic energy, but now you need to solve that, right? All right, so put your board down. Let's write that out. Now, when you solve, there's 3 steps to solving. you're going to start with an elastic energy equation. So E elastic equals, all right, it's equal to 1/2 kx squared. Okay, now we're going to plug, the next step is plugging in what you know. So do you know this amount? How much is it? 10,000. Good. Equals 1/2. What's the K value? It's the spring constant.
Oh, 5,000.
Okay, x squared. That's what you're looking for.
Yeah.
Cool. And then x equals? So listen, just a general problem solving strategy. All right, hold up that board. Just a general problem solving strategy. When you're going to use an equation, you go one equation that's just letters only, then a plugging in, then an answer. X equals? Two meters. I think that's right. You guys did the same one, didn't you?
Yeah.
All right, let's see what you guys did.
We have really same answer. We got 2 meters. I get it wrong. How to fix it?
All right. Tell us what you did.
So for 4, we had all the graphs. We knew it was all gravitational. So then we did the equation for like elastic energy. And like I plugged in all the numbers with the name we had. Then we got 2 meters.
Gentlemen, focus yourselves. So you did the same thing they did.
Yeah.
Okay, good. So tell us about, so that it's, I'm glad it matches. Tell us about 5.
So in 5, we had to find the force to spring. So we just plugged it into the equation and we got 10,000 meters.
Yeah, so one of the things that you guys did in the lab was you developed this understanding of a spring force. How do you find the force by a spring? You multiply K and X. What's the K?
On the spring constant.
It's the spring constant, that's right. And what's X?
X is it the meters?
Yeah, it's the compression distance, right?
Yeah.
So where'd you get the 5,000 from?
We got it from other problem and it was it told us.
Yeah, like legit in number 3 it says the spring constant is 5,000 newtons per meter. Where'd you get the 2 meters from?
Oh, we got it from 4.
That's right. So you see how this thing kind of progresses along where you're gathering and gaining information as you go so you can use it later on? That's the kind of thing we're looking for. That's fantastic. Very, very nice. All right, what do we have over here?
So for number 6, we just had to double the,
Well, what does it say?
oh, sorry. How much force would you have to apply to the spring if you wanted to compress it twice as much? So then we took the variable from 5, which would be 10,000, and we multiplied that by 2, or we did 5,000 times 4, which would be twice the compression distance, and that would give us 20,000 newtons. That's it.
Yeah, actually I like this. So they said if you compress it twice as much, you're going to get twice as much force. And they showed their work on that. I thought it was interesting. You could also reason this one out. What kind of relationship do we develop between force and displacement?
Linear.
That's exactly right. So if it's a linear relationship, if you double the compression, what happens to the force? It also doubles, right? So just a quick aside, we've been working together doing analysis since the beginning of the year, true?
Correct.
And how much of this do we let's graph it, what kind of relationship is it, what does that mean? We did all that so that we can understand things that are new and different for us. Think about a spring. You want to stretch it twice as far? You're going to need twice as much force, right? Does anybody exercise with those stretchy bands? You step on it and you pull it up like this, you pull it down, right? Those are great, but those act like springs too. So if you want to stretch it a little bit, it takes a little bit of force. If you want to stretch it twice as far, it actually takes twice as much force to do that. Right? Think about it, so you can like pull it up like this, or you can pull them wide like this. You want to go twice as far, you're going to need twice as much force. Which I think is a cool idea. What does 7 ask?
While bringing the cart to a stop, does the spring do work on the cart? And we said, yes, since energy needs to go somewhere, it would go back into the cart from the elastic spring.
Oh, so actually, that's really interesting. So that if you think about going in and coming out, we're thinking about just going in. So what's the energy situation right before the cart hits the spring? Is there kinetic energy?
Yeah.
There is, right? But then it hits the spring and the kinetic energy goes to 0, true? It goes into elastic. So the spring converted that energy from kinetic to elastic. And it did that by applying a force. So if you have energy transfer by a force, work was done. You might want to write that down. If you have energy transfer by a force, work was done. Okay? All right? Got one more?
So for number 8, it says, in the real world, friction, both air and track, is a very real issue. After bringing the cart to a stop, the spring pushes the cart back towards point A. Assume that during its whole trip, the cart loses 10% of its total energy. How high back up the initial ramp will it make it? Show your work. So we started with the LOL diagrams, and so we know that the total amount of energy in the system is 30,000 joules. And then we know that it's losing 10% of its energy, so you would take the your total energy in the beginning of the system, so that would be 30,000. And you multiply it by 0.1, giving you 3,000 joules, so you know that's what you're losing to thermal energy. So then you would subtract that from your total amount, giving you 27,000 joules. So then you'd have to plug that back into your gravity, or your gravitational field equation. So you'd have the 27,000 is equal to the mass, which is 100 kilograms, and then times 10 newtons times the height. So then you would divide out 1,000 from both sides, giving you your height of 27 meters.
So I actually really like this. Actually, I like everything about this. But think about it this way. If you started from a height of 30, and you go there and come back, but you lost energy along the way, do you expect to get back to the same height or less height? Less height, right? Because you lost some energy, and then as it all gets converted back to gravitational energy, there's just less there because you lost some of the thermal. How's that? Is that cool? All right, that's fantastic. Thank you so much. All right, you're going to erase your boards here in a second. So tomorrow, I want to assess on this. So you're going to get the B version of the assessment tomorrow, okay? And you'll complete it, and we'll go from there. That sound good?
We're
All right.
allowed to use this.
No. Okay? You may not use this. Now, what I'm suggesting you do, though, is you would study tonight. Right? All right? If you make yourself a study guide, now, just copying this down onto another sheet is not a study guide. All right? That is literally just copying it over. But when you study, you can say, like, things I'm probably going to need to know. I'm probably going to need to know a gravitational energy formula. I'm probably going to need to know a kinetic energy formula. I'm probably going to need to know an elastic energy formula. Right? I'm probably going to need to know how to calculate the force by a spring. Does that make sense? So study tonight, make yourself a study guide, everybody be happy.
And we can use the study guide.
And you can use the study guide, yeah. You can use everything that you've created as we've gone along, except for this that we did tonight. Cool? All right, what are we going to do now? So stay at your stations. We're not going anywhere. Where are you guys going? You guys are running. Don't run away. Don't run away. All right, so here's the thing. Sorry, you see on my post. All right. So here's the thing. So last week, I gave you guys this assessment. It's called Work and Energy Assessment 1. I tried to start grading these, and it was just bad, and I couldn't handle it. And no, it's fine. It has less to do with you than it does with just the general structure of like the school that we're doing right now. So, and then I spilled coffee on it. So that's awesome. So you will notice they are stained with coffee. It's that kind of year, John. It's that kind of year. So they're stained with coffee, and I did not grade them. If you have any marks on them, don't worry about it. Here's what we're going to do. I'm going to give this to you. We're going to do the same thing we did yesterday. You're going to go over them with your friends at your station. Okay? You're going to generate some answers that make some sense to you. Then we're going to go make sure that the answers make some sense to everybody. Then we're going to do an assessment in class sometime next week, and we're going to go from there. Is that cool? Because I don't want to, I want you to know. Like, I care so much less about the grades than I do the learning. And these show that you guys didn't do your maximum learning, so I want to put you in a position to learn something so you understand the world around you better. That's the only thing that matters to me. And then I have to grade you. And it's so dumb. It's so dumb. So I'm going to give this to you. Okay? There you are. You will notice excellent coffee stains. Excellent. I mean, this is just so good. But like I said, I did not grade these. That's for Helena.
Thank you.
Here's some.
So we're not assessing tomorrow?
Oh, yeah.
Oh, yeah, it's so long.
This won't take the whole thing. Now, if you don't get one back, that means you were not here on the day that we assessed, which is something that happens occasionally.
Mine too. Oh, no. My handwriting is nothing.
Now, there are reasons that you may not have been here. Okay, there are reasons you may not have been here.
Yeah.
Oh, you ain't taking it. Yeah, go real fast though, okay? Because I don't want you to miss out on this. Are we going? Are we going? All right. So, here's what I would like you to do. Take a couple moments, all right? Oh my gosh, it's very wet. Yikes. So we got about 15 minutes left. We got about 10 minutes left. I want you to get through this with your people. Start with number 1. Go from there, all right? Write down some good answers. And I will give you 1 or 2 to be responsible for on a whiteboard in a couple minutes. All right? Get to work.
Number 1.